In 2019, the Event Horizon Telescope, EHT for short, released an image of the supermassive black hole at the center of M87 that created and powers the M87 jets. This image represents the first direct visual evidence for a black hole. Basically, we're looking at an emission ring around a dark shadow. This is consistent with the idea that the ring is gravitationally lensed light produced by a hot, turbulent magnetized accretion disk orbiting close to the event horizon of a Kerr black hole, and the dark center is the black hole's shadow. We covered Kerr black holes in the 2019 release of the How Far Away Is It chapter on the Milky Way, as part of our close look at Sag-A-Star, the supermassive black hole at the center of our galaxy. The light recorded was radio light, 1.3 millimeters, which we cannot see with optical telescopes. To create this image, the EHT team chose to display the measured radio light intensity in units of brightness temperature, with orange signifying low-intensity radio light, yellow signifying more intense radio light, and black signifying very little or no radio light. 4 images were created from 4 different days in April 2017. They show movement with stability in the basic image structure. The movement indicates a clockwise rotation in the disk, but there is insufficient information to determine the disk's velocity. Note that the emission ring is brighter on the south side. If we were observing from directly above, the accretion disk would be moving perpendicular to our line of sight. No parts would be moving towards or away from us. We would expect the luminosity to be the same across the entire disk. But from our M87 jet analysis, we found that we are viewing from around a 14-degree angle to the west. This orients the ring in such a way that the matter rotating in the southern half of the ring is moving closer to us, and matter rotating in the northern half of the ring is moving further away from us. It is thought that the southern portion is brighter due to the relativistic beaming effect we covered earlier. This would in turn imply that the disk's plasma is rotating at speeds that are a significant percentage of the speed of light. Here's the measured distance from the center of the black hole to the inner rim of the emission ring. This is the innermost stable circular orbit radius. It's also the photon sphere, where photons can get trapped into an orbit around the black hole. With this radius, we can calculate the black hole's mass. Sag-A-Star has the mass of 4 million suns. M87's black hole is 1,600 times more massive than that, with 6.5 billion suns. This is in close agreement with star rotation studies that put the mass at 6.2 billion suns. Modeling the disk as a rotating charged plasma in a strong and twisted magnetic field under general relativistic conditions, astrophysicists have determined that the spin of the black hole is aligned with the rotation. But again, there is not enough information to determine its spin. For our illustrative purposes, we'll assume that it's 0.9. With that, we calculate the event horizon. It's over 63 times further away from its center than we are from the Sun. Unless it accretes additional energy, matter that crosses this innermost stable circular orbit threshold will enter into a decaying orbit into the event horizon. But we know that the powerful magnetic field near the horizon is capable of accelerating charged particles to near the speed of light and ejecting them at escape velocity in jets perpendicular to the rotating disk. In addition, most photon trajectories into this region will also result in their eventually entering the black hole. This marks the extent of the black hole's shadow. Black hole shadows were expected to be significantly larger than the black hole itself, This one is triple the size of our entire solar system. Here we have traced the peak of the emissions in the ring in order to determine the shape of the image and to obtain the ratio between major and minor axes of the ring. It's 4:3. With our 14-degree tilt, this corresponds to a true circle, give or take 10%. This is what the general relativity theory predicts for co-rotating black holes. And here we have the full size of the black hole and its emission ring. It's 10 times further out than Voyager 1 has traveled since its launch in 1977. This may seem like a very large object, but due to the fact that it is 54.8 million light-years away, it only spans 43 microarc seconds across the sky.